So this is an example of a 2^2 design. We have two factors, memory interconnection networks. There are two kinds of interconnection networks, and depending upon that, the reference, the second factor is the reference pattern. It could be random or matrix. There are other things that were fixed in this study. So number of processors, this was for multiple processors put together in a network. So it's not a core kind of thing, it's a network, interconnection network. And then what interconnection networks did was, I don't know whether they still use them today, but basically connected processors to memory. Many memory banks, many processors. So there are two interconnection networks, omega and crossbar, and depending upon the reference patterns, obviously they change the workload. So the workload could be the random reference or matrix reference, and then the number of processors fixed at 16. Queued packets were not affected but blocked, circuit switching instead of packet switching. So all of these things actually are irrelevant for our discussion right now, but if somebody was interested actually in that particular problem, they will worry about these fixed factors. The factors were assigned -1 and +1 as follows. Crossbar is -1 and omega is +1. Random pattern is -1 and matrix is +1. Now one question, does it matter which one we give -1 and which one we give +1? It should not matter. Basically what will happen is your average will remain the same, the sign may change. Basically whatever is +1 will come out as different sign. So so the thing is, in this case study, they wanted to study three different things. Interesting part is they wanted to study throughput, they wanted to study 90% transit, I forget what n is, but anyway, 90% transit number, and then response time. And so the measured values are, these are the four measured values for throughput. This is for the 90% transit number, and then this is the response time. So they really have three different things going on right here. We could just do one of them and we will have a good example. So if you were to just do throughput, you will draw a table for throughput, and remember the table we talked about last time, which was 4 rows and 4 columns. Actually it will have A, B, AB and I naught and then Y. So 4 plus 1, 5 columns. So you could do that way and then calculate all the parameters. But now we are going to do three different ways, three different things. So let's just do it one by one. If you did it for throughput, you will get Q naught as 0.5725, QA at 0.595, and QB at -1257, and QAB is this one, right? Let's concentrate on throughput for a minute. So this one says the average performance is 0.57. Effect of A is 0.0595, effect of B is -1257, and effect of AB. What is AB? Interaction, right. So the interaction is this much. Now based upon this, we can do two things. First of all, we can calculate the percentage of the variation explained based upon this. And the percentage of variation explained is proportional to QA square, QB square, etc., etc. So you will find that QA, A explains 17%, while B explains 77%, and the interaction is 5.8%. Alright, now let's see what is A, what is B. A is type of the network, that affects only 20%. B is the address pattern, which affects 80%. What do you say? No, the question is the goal of the designer. They are not designing the workload. What are they designing? They are designing network, and the network has effect how much? 20%. 80% depends upon the workload. So that's actually not a very good news for the people who are designing it, because they can't control really the performance that much, at least from this point of view. Alright, and interaction is small, so you can't say that this is good for one kind of network. Interaction is only 5%. or 6% at most, right? So that is for the throughput. If you do n, almost the same result, 20%, 80%. If you do response time, even worse result, 90% is explained by B, the workload. And so this would basically say that the workloads are very different in this case, and they are the cause of all the variation in the results. You see, the total variation is yi minus y bar squared. Out of that, 4 times qa squared is explained by A, 4 times qb squared is explained by B, and 4 times qab squared is explained by C, by AB. So here, if you take 4 times the square of this plus 4 times the square of this plus 4 times the square of this, that would be the total variation. And then, so basically the squares of these tell you what percentage they will explain. If this is a small number, the explanation here is small. If it is, so this one is actually, you see, 2.5 times. So the effect is squared. So it's more like 2.5 squared is 6 times or 7 times. So the rest of the basically the same message is given by different metrics. And that was really a bad news, because on none of the metrics the interconnection networks made any difference. I mean, made difference, but not the difference that one would have expected. All right. So now we are going to extend this 2 raised to 2 to 2 raised to k. There are many ways to extend. Just like we extended regression in many different directions, now we are going to take the simplest design and extend it to 2 raised to k, where 2 raised to k means there are kx factors each at 2 levels. K factors each at 2 levels. So you have 2 raised to k experiments and you have 2 raised to k effects. Out of this, k are main effects, k, how do you say this thing? Yeah? K choose 2, right. 2 factor interaction, k choose 3 factor interactions, and so on and so forth. Alright, let's take an example that will make it more clear. So we have memory cache study. In this now we have 3 factors: cache size, memory size, number of processors. So there are 3 factors. Memory size could be 4 megabyte to 16 megabyte, cache size could be 1 kilobyte to 2 kilobyte, number of processors from 1 to 2. So 3 factors. Now the model would be y equal to q naught plus qaxa plus qbxb plus qcxc. So there are 3 main effects. Then qabxaxb, qacxaxc, qbcxbxc. So there are 3 interactions, 2 factor interactions. Then the last term is qabc xaxbxc. This is a 3 factor interaction. This was not there so far, so this is a new thing that I just wanted to introduce here. So now we have 2 factors and 3 factor interactions, and obviously the main effect and then the mean. So with this model, now you see how many parameters you have. So you have basically 2 raised to 3 parameters, q naught through qabc. 8 parameters. And so 2 raised to 3 parameters, and you will have 8 experiments, because it is 2 raised to k design. You will have 8 experiments, and so the result was that for these 8 numbers are measured. I mean, this is an example anyway. 10, 14, 46, 50, 32, and so on and so forth. We arrange them in a column. We arrange them in tabular form. And the table has 8 plus 1 columns, 2 raised to k plus 1 columns. First we have I, which is always 1. Then we have A, which alternates between minus 1 and plus 1. Then we have B, which alternates minus minus, plus plus, minus minus, plus plus. Then we have C, which alternates minus minus, minus minus 4 times, and then 4 times plus. So those are the 8 combinations. You can write down them 0, 0, 0, 0, 0, 1, and things like that. or actually in this case it is just the opposite, because the first column is alternating fastest. It doesn't really matter which column alternates fastest. You could just do the other way around too. I is just mean. So I is all one, identity. ABC. AB, now this is basically product. AB is A times B, AC is A times C, and BC is B times C, and ABC is A times B times C. So these columns can be obtained like that. Right, so this is vector multiplication. Multiply this vector with this and put the result here. Multiply this vector with this, put the result here. Multiply this vector with this, put the result here. So we just multiply once with that, means we just add them up. That will come out 320. We take A, that means minus 14 plus 22 minus plus minus plus, and then that will come out 80, and so on and so forth. So that is the total row. Since it is a total of 8 rows, we divide by 8, so this is the mean row, and that is 320 by 8 is 40, 80 divided by 8 is 10, and so on and so forth. And these are the effects. This is Q naught, this is QA, this is QB, this is QC, this is QAB, AC, ABC, ABC. If you square them up, these multiply by 8, you will get the total variation. That is one way to get the total variation. Another way to get the total variation is to subtract 40, the mean, from each of these and then add them up. So y minus y bar added up should give you the total variation. First way is that, first way was here, like here, yi minus y bar whole squared. Now there are only, this is 2 by 2 example, but 2 raised to 3 example will have up to 8. So you take yi minus y bar, you take the mean, subtract it from each observation and add up, that will be total variation. Right? Or you can also do 4 times Q naught, QA square plus 4 times QB square, and so on and so forth. The effects, because the total sum of total variation in Y is explained by the model by each of these effects, as we call them. So in this case, if you do 2 raised to 3 QA squared plus 2 raised to 3 QB square and all that, you get 4512. That's the total variation. And this is the division of the total variation. 800 is by A, 200 by B, 3200 is by C, 200 is by AB, and so on and so forth. If you write that by percentage, then 18% is explained by A, and 71% is explained by C, and so on. So if this was the result, then your conclusion would be that the processors are the most important factors. They really affect the performance. 71%. What is the most important thing after the processor? Memory size. That explains 80%, 18%. The total of that would be 71 plus 18 would be 89%. Now do you care? If you care, then you go on further, otherwise you say done. In this case, interestingly, the interactions are not that large. And 3-factor interaction, well, is very small actually. It's not 0, but it's small. Alright, so this is an example of 3-factor design. Now once we understand 2 raised to 3, we can quickly go to 2 raised to k. Very straightforward. And I'm skipping all that 2 raised to k stuff because, I mean, now I can do 2 raised to 4, 5, 6, 7, and you know how to do it. So we are to the end of this chapter, and 2 raised to k design allows k factors to be studied at 2 levels each. You can compute main effects and all multi-factor interactions. This is the first thing that previously you never saw 3-factor interaction, 4-factor interaction, 5-factor interactions, but that can happen. So that is what happens here. The computation is very easy. All you have to do is put the sign table and easy allocation of variation among the squares of the effects. So using the square of the effects. So if you want to find out which factor does what, find out the magnitude, and the one that has the highest magnitude will give you the highest percentage as well because you square it up. right? So then there is a homework and exercise. Homework is this value. Now there are three factors A, B and C. Rather than writing in a tabular form, I have given you in rather than writing in the signed table form, I have given you in another table form. All you do is write them in the proper rows and then get the main effects, interactions, percentages of the variation explained, and sort the variables in the order of decreasing importance. And I am using the word importance very carefully. Okay, importance is not the same as significance. Alright, significance has to do whether this is significant at 90% or 95%, or whether it is zero otherwise. That is a statistical term. Here we are using importance. In the real world, nobody cares if it is 5% or in most cases. In most cases, we worry about biggest things first.